So yeah, tēnā koutou katoa, ko monga kiki te monga, ko waitamata te moana no tamaki aho, ko Joseph Chen toku ingoa, ngā mihi nui kia koutou. Hi everyone, my name's Joseph. I'm from Auckland. One Tree Hill is where on the slopes of the Monga Kiki, or One Tree Hill, is where I grew up. And the Waitemata Harbour was the water. And it's a very warm welcome to welcome you to the statistics crash course. I am a PhD candidate, so take everything you hear with a grain of salt. Yeah, and if you want to leave now, I wouldn't be in the slightest bit offended. So yeah, this course came about as an identification that a lot of people needed statistical support, and as a result, I came up with this course. So let's just get straight into it. So a few introductions. Yeah, just forward, intended learning outcomes, and the timetable. We have 6 sessions, and as you probably would have read beforehand, those are the 6 sessions, the dates and the times. They're going to happen concurrently on Zoom, in person here, as well as a recording as well. And the Zoom link stays the same. This is a bit perfunctory now, online teaching, but nonetheless, if I contract COVID, then yeah, I'll do it from home. Otherwise we'll continue in person. The koha, I'll talk more about the koha later. Okay, goodness, this light is really... I'll talk about the koha towards the end of the thing. Okay, so if you want to contact me, you should have received an email from me, so you can just reply to that. And yeah, so preparation for the course, you should have ideally installed R on your laptop or your computer. Hopefully you brought a laptop for the next part of the session, where we actually do talk through some of the practical things. Installed R Studio, and I've given instructions, and also installed some R packages. Now, if you typed in the command library tidyr, library plier, library ggplot, and nothing came up, you did it correctly. That's all you needed to do. If it came back with an error, then you might want to do something. Then something went wrong. Be prepared to annotate the notes, bring a pen, and yeah, bring a laptop. All right, let's just get straight into it. Okay. So describing data, visualizing data, and data wrangling. So I just want to highlight almost like the basic, the first principle of, okay. I'm just, yeah, okay. So yeah, people on Zoom, if you find myself being hard to hear, just let me know and I can talk louder. So first of all, I just want to highlight the difference between a population and a sample. A population basically is where you know the result of every single person in a population. So, and often in biology, that is not possibly known, and it's impossible, and it's unethical to know that. And in health research, it doesn't. So, for example, if we have the effect of drug X on blood pressure. So the effect of drug X on blood pressure, presumably it reduces hypertension. It reduces it by an average of 10. Now, generally speaking, you can't possibly know this, because this sort of thing, you can't have given drug X to every person that lived in the entire world, past, present, and future. So this is generally speaking unknown. And it's important for this distinction, because often we want to make inferences about a population. So we want to know what does the drug aspirin do to every person here, but we wouldn't have known that had we not already done it. So we use statistics to do that. We do sampling, right? That's what clinical trials are for. So in a sample, instead, what you have is you have something that looks more like this, more akin to this, and effect of drug X on blood pressure. And this part is actually known. And instead, you might have like something that looks like this. And for some people, it increased heart. Can you see that? Okay, I might zoom in. So for some people, it might be, what just happened? Okay, for some people, it might be a bit more, might increase the blood pressure, but you can see that's a sample of 1, 2, 3, 4, 6, 9 people. For those in front, you would like. So, we do we do like males in the class. That's we can when you have a sample and you try to make an inference about the population, you
Joseph, I don't know if you can hear, but you're
sampling.
Breaking in and out.
All right, thanks for that. Hello, hello, testing. Not any further problems. Okay, so for example, the population glasses who are wearing shoes in this, then it makes the more specific you are population, every human ever could not actually possible.
Sorry to interrupt again. It's still all over the place.
Still all over the place. Okay.
Yeah, I almost wondering if it's microphone and head position.
Okay.
See, that was beautiful.
Okay. Well,
oh, maybe not. I'm not sure.
Okay, people on Zoom, can you hear me a little bit better? I'm using my laptop mic now.
Beautiful.
Oh, beautiful. Oh, stop it, you. Okay. Awesome. So basically, first part has been trying to talk about the difference between a population and a sample. The next part is now how do you represent your data, right? So first of all, you could just list all of your data. Oh, you might be hearing double. Okay, people in the room, can you hear me loud and clearly? I hope I've got a loud enough voice, so I might just stick to this so there won't be double. Okay, so descriptive stats. Listing your data. Yeah, so listing your data might be okay if you only have like a few samples.
If you mute yourself on the normal computer, then there's no trouble.
I see what you mean. All right, how do I do this? Okay, lectern computer. Whoa. Welcome to New Zealand's leading university. Okay, well, something almost just blew up. Okay, how do I do this? So that means I need to, okay, room controls. Room controls, no, it's gone. There we go. Okay, we should be good. Okay, nope, still not. I'm muted here, am I not? Yeah, I'm muted. Okay, let's just keep going. Descriptive stats. So you can use something called descriptive statistics to describe or summarize your data. Now, and there are basically two types of descriptive stats. One is measures of central tendency, right? And there are some examples: mean, median, and mode. So for example, if I asked, what do you think the average, well, what do I think is central tendency? What is like a nice way to summarize the heights of everyone in this room? I could use a mean, I could use a median, I could use a mode, although mode might not be as appropriate. And alternatively, I also might want to talk about measures of dispersion, and these are all measures of dispersion. Now, Yeah, so let's have a look below. So measures of central tendency. For example, if we use an example of the number of concussions suffered by rugby players, so if I was to draw 0, 1, well, write it, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say someone suffered it once, someone suffered it twice, someone suffered it 5 times, goodness, and someone suffered it 9 times. So one way you could do this is you could measure the mean of the number of concussions people suffered by rugby players. And how you would do that, mean, is simply just the average, or you just go 1 plus 2 plus 2 plus 5 plus 9 and divide that by 5. And yeah, and that will give you, I think that's 5, 10, 19 over 5, and that will be an average of 3.8, which is roughly about here. You can kind of think of it as like the center of gravity, the center of weight of all the data points. And if you were to do median, the median, it's this middle number. So you'd cross out the highest and the lowest number, and then you cross out the second highest and second lowest number until you reach the middle number, which happens to be 2. So median is like the 50th percentile, or the middle number. And whereas the mode of this data set is also 2, and the mode is predicated by the fact that the most popular number is likely to be the mean number. That's the underlying thinking. Now, as for measures of dispersion, if I just write this up again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and write up the same data points one more time, and except I'll add in the mean this time, 5 and 9. How do you calculate standard deviation? Well, this is quite an important one. Standard deviation, if you just think about it, is the mean distance from the mean, right? The mean distance from the mean. So how do you do the mean distance from the mean? If you just imagine, well, from 2, and this was the mean. We calculated this just before. The mean was 3.8. And if the mean is 3.8, sorry, that was a little bit high. It's 3.8. Well, you just get this distance. You get this distance, and then you get this distance. So from 2 to 3.8 is 1.8, the distance. And then the distance from 1 to 3.8 is 2.8, and the distance from 2 to 3.8 is 1.8. What about the distance from 5 to 3.8? Well, that is probably approximately 1.2. And what about from 9 all the way back to the mean? That is 1, 2, 3, 4, 5.2. If I took all of these differences, all of these numbers that I've just written down, 1.8 plus 2.8 plus 1.8 plus 1.2 plus 5.2, and I add them all together, what am I going to get? And then divide it by 5, divide it by, because there are 5 observations. What will I get? I'm going to get 0 because actually I tricked you. Negative, negative. These are all negative, these are positive, and they balance out, right? And so because they balance out, what do you need to do? Instead, what you want to do is you want to square them. So SD equals negative 1.8 squared plus negative 1.8 squared plus negative 2.8 squared plus 1.2 squared plus 5.2 squared. And then you divide that by 5, right? Does that make sense why we square it? To get rid of the negative sign? Yeah. And then we divide it by 5, then what do we get? What do we get? Anyone? Nope, we get variance. Good on you, variance. And then we have to square root it, and then we get standard deviation. Does it make sense that variance is just a natural consequence of what you have to calculate in order to calculate standard deviation? Sorry, I was being a bit mean and cheeky with that. So my point is standard deviation, it's the mean difference from the mean, except not really, because you have to square it first and then square root it later. All right, so that's quite just a basic concept about standard deviation, right? That's just what we need to know. Variance, you should now know, is the square of standard deviation. And why is it important? Well, it's important because you have to calculate it in order to get standard deviation. interquartile range. So let's start with range. It's just the difference between the highest and lowest. So what's the range of heights in this room? Maybe from 150 to 200 centimeters. I don't know, just the lowest and highest. Interquartile range is a 75th and 25th percentile. So you get the 75th or the 3/4 mark. So, and then the bottom quarter, and then you minus that. And standard error of the mean is, so standard error of the mean, SEM, is standard deviation divided by sample size. Now, this is a little bit of a concept that we'll touch on later. Well, when I say later, I mean next week. It's the standard deviation of the sampling distribution to the mean. However, it's just very popular because standard error of the mean is just a very popular measure that people use. All right, moving on. Types of data. And yeah, okay, types of data. I'm just going to oversimplify it into, well, just so you're aware, there's like quantitative data. Wow, I can't spell. Quantitative data. Then you have continuous data, and this is things like height, weight, things that on a continuum. And then you have discrete data. It's on an island south of Greece. And then you have ordinal data, and then you have nominal data. And now I'm just going to call in some textbooks or in some online resources, you might see this viewed as qualitative data. I'm going to avoid using the term qualitative data because there's actually a huge amount of qualitative research that, it's based on interviews, recordings of people talking and that sort of type, and that's not really what we're talking about. When we talk about discrete data is things that can only take a certain value. For example, I have 4 siblings, but I don't. But if I had 4 siblings, like you can't have half a sibling, so that's a discrete data. Ordinal data is like data that has an inherent set order to it. So for example, if I said the statement, I am cool, and asked you to all on a 5-point Likert scale to say whether you agree or not, that's a 1, 2, 3, 4, 5. A strongly disagree, neutral, agree, and strongly agree. So those are the different types. So that's ordinal data. And then nominal data used for naming. Nominal means to name, and they have no quantitative value. So for example, ethnicity is a type of nominal data, like European, Asian, Māori, Pacific, Mila. And yeah, I'm going to avoid calling anything qualitative data. Okay, are we all following so far? Nod your head or shake your head. Okay, cool. Next, variables and levels. So a key thing to understand is the dependent variable versus the independent variable. Now, the dependent variable is a variable whose values depend on the effects of other variables. And the independent variable is just a variable whose values does not depend on the effects of other variables. We always have this structure. We have dependent variable is dependent on the independent variables. And I want to emphasize that you have variable as a top level construct, but then you also have, now variables can be factors as well. And then when you have a factor like ethnicity, then you have levels within that. So ethnicity might be a factor, but then you also have different levels within that variable. So that variable can take up multiple levels like Māori, Pacific, Middle Eastern, Latin American, or Asian, and other and European. And one of the notations that we'll use for R, the DV is dependent on the IV. How we write that is DV is dependent on IV, and that sign is a tilde. And yeah. That's just the notation you should get used to. The dependent variable is, and then if you want to say the dependent variable is dependent on the main effect of IV1, main effect of IV2, and main effect of IV3, you would write something that looks like this IV1 plus IV2 plus IV3. And then for the dependent variable is dependent on the main effect of IV1, IV, and main effect of IV2, and the interaction effect between IV1 and IV2. And this talks about interaction effects. Then you'd write it something like this: IV1 plus IV2 plus IV1 asterisk IV2. And that is a R notation, and actually it's quite a common notation you have in many coding languages. And yeah. Yeah. And as for interaction effects, I believe we covered that, I think in seminar 3 or 4. We cover it later. Okay, so yeah, the main effect, and again, we'll cover that later, but just introducing you to this concept that a dependent variable like height can be dependent on various things like sex, ethnicity, weight, all sorts of things. And maybe, you know, there might be an interaction effect between those independent variables such that males tend to be heavier than females. So there's an interaction effect between sex and weight. So yeah. Okay, now onwards to types of standardized distributions. Cool. Types of standardized distributions. What are distributions and what is the point of distributions? Now, every population will have different parameters, meaning you can generate infinite amounts of unique distribution. And what we can do is we can normalize all these different distributions to a standard distribution. So let's start off. I'm going to draw up a random distribution. So for example, we might have a distribution that looks like this. So you can see, well, this is based on a sample of people, and this could be, I don't know, this class is IQ, full of very smart people. And so, yeah, that could be this class's IQ, for example, and that is a unique distribution. Whereas we could have another distribution. And this could be another group's worth of another group's IQ, like lawyers or something. Sorry, cheap dig. So yeah, these are all very unique. They're all unique distributions, but we need a way to standardize these distributions, because you could have all the different distributions, you could have all the different populations in the world, but if you have different populations, you can't actually compare it with each other. And that's why we have to standardize it to something. And that's what we call the standard normal distribution. And the standard normal distribution is around, and that is mu, and that's sigma, 1 sigma, 2 sigma. This is the standard normal distribution where, just going to write some symbols first, where the mean is 0 and the standard deviation is 1 squared. Well, the standard deviation is 1, but by convention, you actually call it the variance. Sigma, is that sigma? Yeah, that's sigma. Sigma squared is variance. Sigma is standard deviation. And the standard normal is just that regular bell curve shape that you're familiar with from the central limit theorem. So what we can do, for example, for this, to standardize this, you could minus the mean from here, and then divide everything by the standard deviation. So if you minus the mean, then this would become 0, this would become -10, and this would become 10, and then you can divide the distance of it by the standard deviation. You're effectively normalizing or standardizing, rather you're standardizing the distribution. So for example, this population could be described by a distribution that looks like this, 120, 10 squared. Standard deviation is 10, so variance is 100. Similarly, the lawyer's IQ, it could also be, I don't know, looks like this maybe. And so that's that. Now, there's another distribution that I'm just going to introduce to you as well. What about the binomial distribution? Well, let's say you toss a coin 6 times and you want to count the number of times. Okay, first of all, let's say you flip a coin. What's the average result? Does that make any sense? You can't get an average head or an average tail. What you can do is you can repeat the coin flip numerous times, and then the average the number or get the number or the average times an event occurs. And notice that when you toss up and, I don't know, you get a heads, there's a probability to it, and the probability is 50%. And so, yeah, it's a binomial distribution. There's only there are only 2 possible There are only two possible categories. It either happened or it didn't happen. In a coin toss, it's either heads or not heads. So, for example, in a binomial distribution, it might look like this, and you have to define how many times you did the event. In this case, you toss the coin 6 times, and yeah. And what about the number of people who passed an exam after taking drug X? Let's say you're investigating a cognitive enhancer. You can see, well, did that improve people's chances of passing an exam? And that's just another binomial distribution. Well, yeah. And so what I wanted to say is that what you can do is, from these binomial instances, you can do the binomial approximation to the normal distribution. The binomial approximation to the normal distribution, where you can see how these all look like normal curves, these normal bell-shaped curves. And so essentially, in this case, let's just define this. This is probably number of heads is defined by a binomial variable where you had 6 and 0.5. Oh, I should probably define that. So X is a variable defined by a binomial distribution of N and P, where N equals number of trials and P is the probability of the event happening. And so you can do the binomial, so that is like the standard binomial, that is a binomial distribution. And when you do the binomial approximation to the normal distribution, if you want to change this into a normal distribution, you can do this by doing X, i.e. the number of times the event occurred is now normally distributed as N times P, comma, NPQ, and where Q equals 1 minus P. So if we go back to this one, the coin toss, oh, you can't even see that, my bad. Oh, yes, you can. The people on Zoom couldn't. Okay. So if, for example, the binomial distribution of the coin toss situation, X is dependent on a binomial. How many times did you do this? You toss the coin 6 times, and what's the probability of heads? It is 50%. If you were to change this into a normal distribution, X would then be a normal distribution where 6 times, there are 6 events times by 0.5, and that would become 3. So you're expecting 3 heads, and that's kind of what you expect, right? It's your average number of heads in this experiment will be 3 times, and then comma, the standard deviation will be N, 6 times 0.5, and then Q is 1 minus that. So so P is a probability of heads, or P is probability of the event, and Q is a probability of the other event. Because a fair coin toss is 50%, it's just 6 times 0.5 times 0.5, and that would become the standard deviation. Yeah. Now, I talk about this because in quantitative statistics, we often have these types of factors. We often have, did this person survive the surgery? Yes or no? Did this person improve? Yes or no? Did this person whatever? And so that's why we often use binomial related distributions to do this. So that's why. Now, that said, there are a lot of other different distributions which you'll come across, and yeah, good luck. Yeah. Moving forward, swiftly onwards. Inferential statistics. So inferential statistics is going back all the way to what I was just saying at the very beginning, population and sample. When you make an effect of a sample and you're inferring what it will do to the population. So in inferential statistics, now we need to introduce another concept called the null hypothesis and the alternative hypothesis. So the null hypothesis is when there is no difference. So mu1 equals mu2, whereas the alternative hypothesis is mu1 is not equal to mu2. Now there are things as tailedness, like a one-tailed test, meaning that, oh, mu1 is greater than mu2, or mu2 is greater than mu1. For the purpose, I can talk more about that if you'd like, but please never do one-tailed tests. Just stick to two-tailed tests, because it's just not okay. Unless in unique circumstances, but most 99.9% of the time it's not. So yeah, a null hypothesis, there is no difference, and an alternative hypothesis, there is a difference. Now, we just so happen to believe that if p is less than 0.05, that's quite an arbitrary number. If p is less than 0.05, that is the standard threshold of evidence. So now I'm going to introduce another concept called, I should explain more about the null hypothesis, right? So let's say in this room, let's say we had no idea about the heights of males or females. And I'm just going to say, okay, I think males are generally taller than females. And in this room, I could measure everyone's height, and then I could find, okay, what was the difference, right? If this was just the population, then yeah, I could say males or females are taller than one or the other. I don't actually know, but if we were to say, if I did this experiment where I measured everyone's height, and then based on this data, I extrapolated to the entirety of New Zealand, that would be what we call statistical inference, when you're taking from a sample and inferring to a bigger, wider population. And yeah. And so then you have a null and alternative hypothesis, where these two are supposed to encapsulate the only possible possibilities, i.e. it is the same or it's not the same. Therefore, the probability equates to 1. So now I'm going to introduce something called type 1 error. Now, type 1 error is the probability of detecting a difference when no true difference exists. So, and as I was saying, and type 1 error rate, sometimes notated as alpha, is the probability of making a type 1 error, and that's usually 0.05. And so if we ran, males are taller than females, and then we got the numbers, I don't know, average height for males, 170, average height for females, 165, and then we did a t-test, we'd get a p-value. Let's say the p-value was, in this case, 0.016. What we're essentially saying is, as the probability of seeing the current results is 0.016, it's below our threshold of 0.05. Therefore, there is enough evidence to reject the null hypothesis in favor of the alternative hypothesis. What it's just saying is that, presuming the null hypothesis is true, by assuming the null hypothesis is true, that there is no difference, it's saying that the likelihood of seeing what we just saw is only 1.6%. And because there's only 1.6% chance of that happening due to chance, we think that's not possible. That's unlikely. Therefore, we call this a significant result, and then we publish. And then if your p-value is greater than 0.05, say 0.796, then we say, well, if there's an 80%, well, a 79.6% chance of that occurring, if there's a 79.6% of chance of that occurring, well, that's pretty good odds, right? That's, of course it's going to happen. It's not particularly remarkable. So therefore, we accept the null hypothesis and we reject the alternative. And then in scientific journals, we'll call that a non-significant result. And then you get the weirdos that like, oh, p equals 0.09. Oh, it's approaching significance, which we won't talk about, but let's not do that. All right, common statistical notations. Mu, we use a lot of Greek letters, and so mu is the mean of a numerical variable. Now, I just want to highlight there's a difference between the population and the sample. In the population, we use these Greek letters, whereas in the sample, we use slightly different letters. You'll note that when I talk about this, the null hypothesis, there is no difference between population 1 and 2. Going back to my example of males versus females in this room, the height of males versus the height of females, is that provable? Can I prove that males are taller than females? Yes, because I can literally grab a ruler and measure every male and then grab a ruler and measure every female. Like that's something that's actually doable. Whereas, so when we talk about hypothesis, we're always talking about the population. We're never talking about the sample, because in the sample, you actually can, right? Let's say you ran a clinical trial of 100 people, you literally have the results, even though the average height of males, the average blood pressure decrease was 10 millimeters mercury in your treatment group and the control group was 9 millimeters mercury improvement or decrease, you can literally say in your sample, drug X improved greater than the placebo. And that's technically true, but it's just when you're trying to infer that to the population, that's where the statistics comes in. That's when you have to run the statistical test. So that's what I want to reinforce, is that when you talk about null and alternative hypothesis, be careful. We're talking about the population. We're not talking about the sample, because you know what the sample results are. And so, yeah, so mean is often called mu. And we often call it X bar for the sample, X, and that's, you would have seen me write X bar in an earlier situation. Sigma is the standard deviation, the population standard deviation, whereas S is the thing. And you might have seen me write S squared, and S squared is to denote variance. And then pi is for proportion. So for example, what is the proportion of heads? What is the proportion of the expected number? What is the proportion of heads in a coin toss experiment? So pi equals 0.5. That would be a use of it. Rho is correlation. So we'll later talk, I think in seminar 5, we'll talk about correlation. Yeah, and then beta is the gradient. So y equals mx plus c. If you remember back in high school, y equals mx plus c. That's also, they often, the m and the c, they often use beta to denigrate, to call that, to denote that rather. And theta is just general usage for anything that you don't know. And epsilon, the Greek letter of epsilon, is just something, error, is often just used to denote error. Okay. Now, we also need to introduce another concept called degrees of freedom. So the more degrees of freedom you have, the more American you are. No, I'm kidding. No, so if you have 100 samples, you have 99 degrees of freedom. And I don't really have a good way to explain it, so just accept it and move on. If you have n samples, you have n minus 1 degrees of freedom. If you have 1 sample, you have no degrees of freedom. If you have 2 samples, you have 1 degree of freedom. If you have 20 individuals in 3 groups, and so if you have 20, 20, 20, you have a total n of 60, you have a total of 59 degrees of freedom. Now, and the general traditional thinking of that is that depending on the test that you do, you can use 1 degree of freedom to conduct 1 test. And it's a bit of an abstract concept, and I wouldn't worry about it now, because as you go into more statistical theory, they do, you have to correct for the degrees of freedom. But general thinking is that if you had 5 groups of people, you should only be allowed to make 4 comparisons, right? So you can't just keep on chucking these out. So degree of freedom, yeah, it's a bit of a weird concept, but just accept it, move on. Yeah. Any questions? No? Yeah, great, fantastic. Types of data. All right, so as part of this course, what I really thought was missing in a lot of these courses was actually being able to publish your data and just like actually making a graph. So part of this course will also go through some code as to how you would actually code up a graph and actually, like, as if you were going to submit it to a journal and actually, you know, incorporate like design elements in a graph. Okay. So, for example, I'll start with a basic histogram. So it's very bright. Lamp. Is that better? Barely. Okay. Anyway, let's talk about a histogram. So, I think I remember learning about this way back. So, okay, histogram. So let's say we wanted to measure height. So it'd be like 160, 170, 180, 190, and it's just bars. So it just measures the count of the variable. So let's say if we have 5 people in the 160 to 165 bracket, and then, I don't know, 10 people in the 165 to 170, it's only a measure of count of a single variable. It's a way to describe the distribution of a variable. So you note that there's only one variable that we're talking about, and this variable is height. What about box and whiskers plot? Well, on the y-axis is a continuous variable, whereas on the x-axis is typically a discrete variable. In this case, it is a nominal variable because males and females, that is a nominal variable. We name them. And so we can have something that looks like this. And maybe something that looks like this. Now I'll just quickly write these. There are 5 things that you need to point out. So the top one is the highest value or the largest value. And then the second top one is the upper quartile. So the 75th percentile or the upper quartile. The middle is not the mean, as is common the mistake. It's actually the median. The lower one is the lower quartile, and the lowest one is the lowest value. So a box and whiskers plot essentially summarizes 5 bits of information into these. And yeah, so you can see on one side, it's a continuous variable against, on one side, it's a continuous variable against a nominal variable. So there are 2 variables in which this can map, which is pretty good. Now, another type of plot is a bar graph, continuous, to just say, that's supposed to write continuous. And again, you can represent the same data from the bar graph, from the box and whiskers. It can look like this. And in the future, also, what do the bars represent? In your figure captions, you'll need to write the bar represents the mean, whereas error bars represents whatever you want it to represent. It's typically either SEM or SD. SEM being standard error of the mean and SD being standard deviation. Now, please, in the future, try avoid using these bar graphs or column graphs, or some people cheekily call it a dynamite plot because it looks like a plunger, like you're plunging a detonation device, because they actually hide the data. You can see it, the only bits of information it shows about the spread of your data is the mean and standard error, or the standard deviation, depending on what you choose. At least in the box and whiskers plot, you have 5 bits of information on there. Right. That said, it still remains an incredibly popular graph type, which, for better or for worse, will stick with us for a while. Next up, we have scatter plots, and scatter plots are great. I love scatter plots because they are great. Did I say that already? Okay, so they're continuous against continuous. Notice how the previous one was continuous against discrete. Now this one's continuous against continuous. For example, height against weight, and then you can see this. So you can see it's a continuous variable against a continuous variable. Furthermore, scatter plots can also, they're quite versatile. You can do a continuous variable against a discrete variable. For example, males and females. And what you can do is something that looks like this, where you have to state in your figure caption, dots represent the mean, and error bars represent the standard error of the mean or the standard deviation. However, this has the exact same problem as bar graphs. They hide data, so try to avoid doing that. And as we go through the course, I'll show you other graphs that you can do to get around that. So yeah, so that's a continuous against discrete. And yeah, now the other cool thing about scatter plots is you can also do, okay, I'm just going to reproduce that graph just then. Continuous against discrete, males, females. And let's say you had this. Now that's a very common sight to see, but you can also add a different color. Okay. Oh, you can see it. Okay, great. this isn't a black and white camera. Okay, great. So maybe you can now use color as another dimension. So you can say, I don't know, this could represent elves, red equals elves, blue equals dwarves or something, I don't know. You can have another dimension added to your graph and it displays more information. So, yeah, so just being mindful of there are lots and lots and lots of different types of graphs that you can use to display information. Yeah, so now I really want to hone in on the dimensionality, the data visualization side of things. Okay, so just going back to basics. So this one was height, this one was weight, and this was 2D to 2D. And when I say 2D, I just mean it's just height against weight. It's just under 2 dimensions. You can see height and weight. And typically when you're reading a journal article, it's a flat piece of paper. There's only ever 2 dimensions to it when you're doing spatial dimensions. It's just on the y-axis and the x-axis. You can't really go depth, not really. However, you actually can do 3 dimensions by doing the trick that I just mentioned. So for example, height, weight, and then if you did, that would be the human trail, and maybe this could be in color in red. That's the dwarves, yeah, sure, dwarves. So now this is a 3-dimensional plot. Why? Because you have 3 dimensions. You have one on the x-axis, you have one on the y-axis, and you have one on the color axis. All right, I just want to introduce that. You're now adding another dimension to the graph. And then let's go even further and go 4D. I'm going to break the space-time continuum. Okay. So for example, this could be you can have dots to represent females and crosses to represent males. And so in blue is the humans, in red is the dwarves, and then dots equals females, and then crosses equals males. So now we have 4 dimensions on this plot. So yeah, just want to illustrate the fact that, yeah, it's just think about, be mindful of the number of dimensions you add, because the more dimensions you add, the more complex and the more difficult it is to interpret these results. Going through a bit of digital jargon, yeah, so first of all, 300 to 500 DPI. So typically when you're submitting to a journal, they'll probably either specify DPI or a vector type. So DPI stands for dots per inch. And what does that mean? It's just how finely resolved, how many dots or how many pixels are in there per inch. So it's a measure of like resolution. And there are so many different data formats: TIFF, PDF, EPS, JPEG, PNG. Which file format should I save as? If it's a photograph, typically you'd want to save it as a TIFF. Now that's just what I've noticed from a lot of journals. They often ask for it in TIFF. If it's a graph or if it's line art, typically save it as a PDF file or an EPS file. And that's, again, based on my experience with publication. But of course, your publication requirements will be different from mine. Yeah. Now I just want to highlight the difference between raster and vector images. Raster images are like photos or images, and all of these are types of raster. And so you can see like this photo of a cat. You can see I purposefully made it really grainy, right? You can literally see pixels in the such way. And so that's what a raster image is. And the problem with drawing a graph is that you don't actually want this distort, like, because if you save and zoom into a graph, you're going to start seeing these distortions because this is a raster image. So instead, you actually want something, a highly resolved vector image. A vector image is not going to be photos. It's going to be likes of drawings, cartoons, and line-based art. So when you zoom in, what you see, the computer will recalculate and make it highly resolved. That said, because I printed this and it's in front of you, no matter what, it is going to be raster, because if I look at it under a microscope, I will be able to see individual pixels. But that said, in a computer setting, when you zoom in, it should have infinite resolution because it's actually a mathematical line. So that's why you should always save as vector if possible, because that way your file sizes stay small and manageable when you're trying to upload things to the portal sites and such like. So yeah, unless if you're doing like histology, if you're like publishing a nice electron micrograph or a nice slide of something, then of course you'll have to be doing raster-based stuff. Okay, cool. Any questions so far? No, great. Oh, sorry, no? Okay, cool. Last but not least, data wrangling. So I will say that data wrangling and tidying up your data will take up 80% of your time. This means getting your data into a format that can be analyzed. Yeah, more often than not, typically speaking, I think most people will put their data into an Excel spreadsheet. And yeah, and so we'll go through that in the next part of this to talk about how to do that and to input it into a data analysis software. Principles of good data organization. In your Excel sheet, avoid using anything but alphanumeric text for information. For example, highlighting cells. Okay, now I actually don't know if it translated very well, but some of these cells are highlighted or are supposed to be highlighted. Yeah, I don't think they were highlighted. Anyway, so avoid highlighting the cells and then presuming, oh, what does a highlighted cell mean? I don't know, it could mean anything, right? So try to avoid highlighting cells because it doesn't save very easily. You can't really, like, how do you add highlight in there? Avoid using capitalization. Avoid using spaces, and if you want to use a space, use underscore instead. Now, the reason why you want to use that is because you can actually see the underscore, and we'll talk about that soon. If there's weird non-applicable data, just leave it as NA, don't leave it as a question mark, because as I said, leave it as alphanumeric, so letters and numbers. If you leave it as a question mark, depending on the software that you do, it might blow up it might just corrupt your file. If there's missing data, leave it as null, don't leave it as empty. If you put it as empty, you might be like, wait, why is it empty? Did I forgot to put it in? Oh, wait, no, it's because it genuinely is missing, right? So if you know it's missing, just put it as null, type in NULL. Aim to use numbers to represent factors, for example, 0, 1 for male, female, or 1, 2, 3 for whatever, 1 equals something, 2 equals something, 3. If you have multiple ordinal levels within a factor, aim to ensure that it's in alphabetical order. Compare this, so A underscore very low, B underscore low, C underscore medium, D underscore high, E underscore very high. Whereas if you organize that alphabetically, it become high, low, medium, very high, very low. It's because R doesn't necessarily know how to order your data, but you do. And so if R will default to just organizing your data alphabetically, which is what I've purposely done here, H, L, M, V, and then yeah, VL. So take, for example, this data set, which will be in the thing that we talk about later. Notice how NZ European, that's already a problem. R will think these two are different values. So that's why, because there's a space there, maybe you could just do European or lowercase or something, just as long as you know in your head a consistent framework in which you're going to run things. Other problems are, oh yeah, the M and the M. So little m and big M are different when coding. And this is consistent across almost every statistical and analytics software, that a little m and a big M will be different, will be considered different. So be consistent. It doesn't actually matter if you use capitals or lowercase, as long as you do you, as long as you are internally consistent with your data. My preference is to use lowercase for everything. But yeah, it doesn't actually matter. So make sure you make sure you just stay consistent on certain things. Now there are certain, I think I highlighted this cell. if it's been highlighted, and the thing is, see, I've often received data from my colleagues, and they're like, Joseph, can you analyze this data for me? And then within that Excel spreadsheet, there's like random bits of things that are just highlighted. And I'm like, well, why is it highlighted? There's no information. So instead, in the future, if you just add an extra column and call it something like notes, and just type freely into it saying, that highlighted cell is a bad reading or something. Just add to the side and just type in bad reading, or that data point is not reliable because XYZ or something like that. So yeah. So that's the principles, that's some guidelines on how you should organize your data. Understanding the wide and long format. So this becomes a problem whenever you're recording a person more than once. So for example, in this example, or it's a different example, we are actually recording a person number 1, their height is 169, and we're seeing if they had COVID in July and if they had COVID in September. So person number 1 did not have COVID in July, but they had COVID in September. And so you can see how, well, this, in the wide format, it keeps on expanding to the right, because every time you add another observation of a person, you add it as another column to the right. In the wide format, this generally assumes each row is one individual. And so, as a result, it becomes a very wide table because you keep recording more information about one person. However, in the long format, what you do is, do you see how in the same person, you still have the height variable. It's still the same height. They haven't changed height, but now you have a time variable, and the COVID July, COVID September, and then COVID status 0, 1. And so instead, in the long format, if you have another observation, usually varying across time, you just add it as a next time point going down. And so it becomes a very long table with many, many rows. So that's the two different ways you can organize your data. And so, yeah. All right, so now's the funner part, and we can talk more about how to play with R, which is much more interesting. Okay, so in this section, so I'm going to be looking, so I'm going to share screen, and I'm going to share what's on my laptop, but I will be referring back to the course guide, but I won't be writing in the course guide anymore. So now I guess is the time when we, okay, so someone asked on Zoom, what is the significance of wide versus long in R? You'll see. Okay, so let's move on to, okay, how do I stop sharing? And now I want to share screen. Oh, okay. Right. Here is a photo of a cat. Okay, so do we want a break? Are we good to keep going? A break? Oh, sorry. Who wants a break, or who wants to keep going? I think more people want to keep going. Okay, let's just get this over with. Okay, so introduction to R, guided and a studio. Okay, this is really testing. Okay, interesting. Okay, oh no, it's still there. Oh well. No, I'm muted. Yeah, it's muted. Yeah, I agree. Okay. Hello? It sounds like it's coming from down there. I don't know why. Okay, so first of all, I wanted to open up R. Now, if you open up R, this is actually what R looks like, by the way. This is like base R. Let me just hide this. Put that in the corner. And let me just hide this. and put that in the corner. Okay, this is what R originally looks like. And this is what you can do stuff, and you can just type things, I don't know, A equals 10, B equals 5, A plus B equals 15. You can use it as a basic calculator. Now, yes, R base, also you can open a script, and if you go to desktop, what is this desktop? This desktop. Where did I put my stuff? Course code. I'm going to open up StatsCC Seminar 1. So first of all, I already have pre-written some code for you to run through. Now, what I could have done is, okay, 1 plus 2, okay, copy, and then put that, paste, enter, copy, paste, enter, Control C, Control V, enter. You can see how that gets quite annoying. So instead, R was like, okay, well, why don't we just have this button? And if you run this line, it runs it for you. So now I can just run multiple lines like using this button, and it just runs it for you. But then at the same time, people were like, no, but this is still so clunky. We want something that's a bit more streamlined. And so that's why we don't use R original. We now use something called R Studio, which actually I have down here. So I'm going to boot up RStudio, and hopefully you should have that already installed. And yeah, okay, so it opens typically up like this, and you should be familiar with that. It's got some environment stuff that you can put into here and some plot stuff over here. I should have explained back when I had R open, sorry. When I had R open, I also just want to show you that this is the R console. The R console is where you actually input all your commands that you want to be run. And yeah, and then the script file that I opened before, that's a script file. So going back to RStudio. So now let's open up the file that I sent through. Did everyone manage to find that file okay? In the course code and Seminar 1. So it should look something like this. It was sent to you, and it was in the Google Drive. And within the Google Drive, there is a folder called course code. And within that course code thing, there is a whole bunch of documents. All of those documents I've downloaded and put in here. And I have opened up this. One thing that might be helpful is if you right click and then do like properties, you can opens with what? I think the default in Windows 10 or Windows 11 is that it opens up as a text file, but I changed it to open up in RStudio because these are R.R files. So that's why you can do that if you want. Okay, so a few things is, first of all, if you haven't used RStudio before, I strongly recommend you to do the following. So if you go Tools, Global Options, then go to Workspace, Workspace, and then save Workspace to R data, and click Never. Okay, my instructions are wrong. It's actually slightly changed. R is under constant renew. RStudio is under constant renewal. Actually, RStudio is changing its name soon. Sorry, I should have probably let you guys know, but I think as of November, it's going to be called something else. Does anyone know? It's going to be changed. It's the creator of RStudio. It's still going to be free and everything. It's just going to have a different name. But yeah, it's going to change its name. But yeah, okay. But yeah, I'd recommend that you save Workspace to R data on exit, put it to never. Now the reason is it means every time you open RStudio, it's a fresh reset. It won't remember everything you did previously. I strongly recommend it because it makes your pipeline, your analyzing pipeline, much more reproducible, and that's an important facet of science. And click OK. Okay, now also, what did I say? Source. Click the script button next to source. Next to source. Okay, I don't know why. All right, now my next thing was click Tools, modify. Hello.
We don't know which file it is.
It would be. Yeah, sorry. Yeah, by the way, if you are lost, please do let me know. Yeah, like so there should be these files that are found on the Google Drive. Within the Google Drive, there should be that.
Am I surprising? Okay, who has found these files? Yeah, okay, some people have found them. Okay, so yeah, within them, and then StatsCC _ seminar 1 is the file that I'm using today, because today's seminar 1. Awesome, no worries. Yeah, but please do let me know, and as well as on Zoom, if you do want help. Now, the other one I would recommend, actually, you don't need to do, but I do. Tools, modify keyboard shortcuts, and I'm going to search for run current line or selection. I've changed it to F9. Originally, it's Control Enter. I prefer F9 because I'm coding MATLAB, and F9 is convenient for me, and it's easier pressing one button rather than pressing Control Enter every time. But yeah, that's just style if you want to do that or not. You certainly don't have to. Okay, now we're going to run through the basics of R in this. So for example, over here, this 1 + 2, I can just click over here, and then all I do now is I press F9 and it runs in the bottom left. So you should have seen what happened on the top left. I clicked on 1 + 2, I pressed F9, and then on the bottom left on the console, it put it through the console. All right, that's what you can do. Alternatively, you could just type everything out. 3 + 6 = 9. Log 49 minus square root 4.2 is that. Oh goodness, wait, people on Zoom, you're going to be annoyed by me typing, aren't you? Sorry, team. I should have brought headphones. Okay.
It's okay, Joseph.
Oh, it's fine. Oh, okay, great. Okay, great. People said it's okay. Sorry, team. Yeah. Okay. All right, so assigning R objects. Now it's important to note that we can create objects in R, and it's something as simple as this: pandas = 5. So that means when you type in pandas, you get 5. So you're just assigning an object. Now, in some schools of thought, they prefer you to do this. They prefer you to use like an arrow thing. Pandas is that, and then you can do, oh, oops, typo. Yeah, I'm lazy. I prefer pressing 1 key rather than 2 or 3. So yeah, I'll stick to my equal sign. And then giraffes = that. And then you can do simple multiplication, pandas times giraffes, and that gives you 10. Now notice that pandas times capital G is an error because of that capital G. That capital G, as I was saying before, R is case sensitive, so that it shouldn't be a surprise that it did not go through. And then, yeah, we can go through all of these things. You can like have character data. So an R character object looks like this. So for example, if you went R character, okay, no, never mind, ignore that. But you can have character. Within that R character object, it's called puppies. And numeric data can be saved like that. And I'm just saving it as R numeric, and that just becomes a number. And what about R logical? R also accepts logical data. So it could be R logical becomes true. An object called R logical is true. Let's call cat equals, if I just call it a capital T, cat will also be true. So R also reserves capital T and capital F to represent true or false. An R factor, you can also call something a factor, and a factor variable, oops, it just becomes an R factor variable. So we can also save things as vectors. Vectors are objects which have multiple values in them. And R has this property where vectors can only contain one type of information. And so if you had ID, for example, ID contains only character data. So ID equals letters, only, well, essentially letters. You can also make numbers into letters as well. So for example, if I went lemons equals 1, 2, 3, 4. So lemons right now would be a number, but if I went lemons equals, in quotation marks, 1, 2, 3, 4, and then typed lemons, lemons would now be no longer numbers. The number 1,234, lemons would now be a string of letters of 1, 2, 3, 4. But let's go back to this. ID equals that. And then I'm now pressing F9. Height equals 167:169. So what does the colon do? Can you guess? What does the colon do? The colon dehydrates gut contents. Oh, sorry, wrong course. The colon just helps bridge the numbers, right? 167 to 168 to 169. And then sex is, yeah, so it's saved 3 letters, M, F, M, in this case, male, female, male.
Wait, sorry. When you say bridge numbers, do you mean like, say it was 168 and 170 with a colon in between, it would include all the numbers that you're missing out, like with groups?
Absolutely, you can, yep, 160, wait, to 170, just go 168, 169, 170. And you can go 1 to 100 really, and I'll just keep doing that. And 1 to 1,000. Oh. And so forth, and then omitted many entries. So yeah, so now I've got these 4 vectors, and notice how all of these vectors are 3 elements long each. Now I can put them into something called a data frame, and data frames are like the workhorses of R. So I've now combined them into a data frame, ID of these. I pretend that these are like the NHI numbers, the height in centimeters, sex, and then COVID, whatever. Now you can do something called subsetting. Let's say you only want to draw certain data points out of it. Now, always think of like row columns. So you can use these square brackets to denote subsetting. And so, oh, I should have been making this bigger. Ah. Can I make this bigger? Oh, I'm sorry, team. Okay, well, you'll just have to squint. Yeah, so RDF3. So when it says 2, 3, it means row, column. So if I pressed F9 in that, what do you think the result would come out as? So the second row and the third column. So what element of this data frame would come out? Yep, absolutely. F, because the first, this is the, so the second row, so we're looking at this row, and then the column is the third one, 1, 2, and then sex is the third column. So F would come out. So you can do something like subsetting, and so subsetting is quite versatile, really. So you can go 2, and then if you just leave it blank, it just will return all the values of 2. If you leave it blank, it assumes you want all of them. Yeah. You can also use the $sign. The $sign just means, from the data frame random DF, I want the factor called ID. And so it gives you all the IDs from that. So that is another thingamajig, another way to subset data. Now for exercise 1.2, this is where we get into, more practical things. So I already asked you to install these 4 packages. If you haven't installed them, you can type in a thing called install.packages, and then you can type in, and now you have to type in this command, install.packages tidy apostrophe or tidy R, but actually I've already installed it. I've just asked it to reinstall it, but that's fine. Now, but anyway, if you've already installed it and you want to call the package, you have to call it at the beginning of every session or before you run some of the things. So all of these packages, all they do, they are a collection of commands, useful commands that add to your experience in R. So they have a lot of useful commands on helping you build a nice graph, for example. And that's why we use these packages. And in fact, many, many people around the world all use these packages. So yeah, if you want to use their commands, you have to run the library command, library, open brackets, command, the package name, and then close brackets. And if that comes up with an error, then you might not have installed it, in which case please install it and then do it. So now in the first part, okay, we have in exercise 1.2, it says you have completed a retrospective audit to determine whether drug X versus no treatment will impact systolic blood pressure during the day in a cohort of patients in intensive care settings. You have reviewed the systolic blood pressure data from 200 patients at 9 a.m., 12 p.m., 3 p.m., 6 p.m., 9 p.m., and additionally collected age, sex, ethnicity, and the patient's PUMP196 genotype, either A, C, or G. Okay, first of all, let's just look at the data. Always, number one, look at the data. Now it's in the file that I sent. Notice that it will be called seminar1_df1. DF stands for data frame. I'm going to open up the Excel worksheet, because as I said, you probably save your data as Excel sheets first. So I'm going to open up the Excel sheet first. And it's loading. Okay, so this is what the data looks like. Needless to say, this is all made up data, so please don't think these are actual NHI numbers. Okay, so you can obviously see there are a few problems here. If you zoom in, you can see this sex. Oh, right, I've given you my master file. Oops, I shouldn't have given you this file. Okay, no, sorry. Ignore it. Don't open your Excel spreadsheet. Open the CSV file. If you open the Excel spreadsheet, you'll notice that there are formula in there, and the formula was the ones I used to generate random numbers and random data. But yeah, we're going to open the CSV file instead, and we can collectively correct some of the mistakes that were made in that CSV file. Now, what does CSV stand for? CSV stands for comma separated values. Unfortunately, if you work with Europeans, their commas are sometimes apostrophes, and so their CSV files might not work as well in New Zealand computers. So yeah, just bear that in mind. Our CSV files may be different from international CSV files. Unfortunately, we use CSV files pretty generically. So yeah. Okay, so now if you just look at the sex column, you can see there are quite a few issues with that. There are some capital M's and little m's, capital F's and little f's. So what you can do is you can select this, and then you can go Control F. This is what I do when I'm trying to clean the data. I'm just showing you what I do. Find and replace. Now I want to find all the capital F's. I'm going to match the case because I want to replace it with little f. I want them all to be the same. This is how I clean my data. And I want to match the entire cell contents. I don't want anything else. For example, there's probably an F here in the ID column. We don't want that too. I want to match the entire cell contents, and I want to replace it all with little f. And replace all, it's all done. We made 45 replacements. Now we've also got the same problem with big M. I want it all to be little m. And similarly, I replace all done. And then what do? Are you done? No, you look through it and you look, wait, why is this one still capital F? Why is that still capital F? Didn't I just go through and replace all? Well, and this is a bit cheeky of me, if I double click into it, do you see the problem? There's a space in there and you cannot see spaces. That's why you always use underscores, right? And because there's a space in there, when I tried to match the cell content, nope, there's an F space. Whereas in my instructions, I told it to do F, no space. And so that's why, please remember, just try to do that. And so I just manually correct that into F. And I know for a fact, because I made this, that I think there's another one later. No, I think I'm done. Okay, that's good, nice and clean. And then the ethnicity looks just like a mess because there's capital problems. Yeah, whereas all the other data looks largely okay. Okay. So most of the data looks okay. I'm just gonna, can I ignore the ethnicity data? Yes, it looks like I can. So I'm just gonna save this. Now, if this was an Excel file, what you'd need to do to load it into R is you need to go File, Save As, File, Save As, and then Save it as. And then you need to drop down. On the drop down menu, you wanna do CSV, comma delimited. So that's how you would export an Excel spreadsheet into a CSV file, right? So that's what you'd want to do. You want to save it into a CSV file in order for you to import it into R. I know it's a long, annoying process, but Any? Yeah. Press Control F or Command F. I noticed you're using a Mac. And then it says find, but if there's another tab for replace. Is that right for Macs? Great, fantastic. Okay, so that's what you do. Now I've already saved this, so I'm going to close it. And now I'm going to go here. So choose a working directory. Now, notice how there's so many things down here. I don't actually want to see this. I'm just going to press Control L and it's going to be nice and clean. And also I'm going to delete all the previous things that I already input. RM list equals ls like that. And it just deletes all of these. If I press enter, it deletes my environment. What you could do instead is just simply close out this, close everything, and then reopen it. And that gives you a nice fresh start. The reason why you often want to be able to close it is because just if your computer crashes or something, you need to make sure your data is reproducible, your analysis is reproducible. Okay, so let's go back. And now because we restart the session, we need to input the libraries. And so, yeah, there we go, libraries. Now, first of all, we want to save it. So the easiest way is to I want to put it into my desktop folder, which I called course code. And course code, that is, if I just press that thing, I can see that is the whole, actually it goes a bit further to the left, C/users/JCCH OneDrive desktop course code. That's where I want to set the working directory. I'll explain what the working directory is. So what I want to do is I want to set the working directory and set it like that. Oh, okay, never mind. So first of all, you can get the working directory. And the working directory is currently C users JCCH OneDrive documents. That's where the working directory is. So when you say look for this file, it will look for it in that folder. And when you want to save a folder, something, it will save it. R will save it in that folder. But often when you're running your own experiments, your data analysis pipelines, you're going to want to save it in a certain folder. And so that way you'd need to choose which working directory it is. So one way you can do it is using this output directory equals choose the directory, and then in desktop course code. That's what I did. Now, if you're using a Mac, I don't think this command works, and I'm sorry, I don't really know the equivalent because I only have Windows. But otherwise, another way you can do it is simply go output _ directory equals C like that. Except this time you need to go through and change you have to reverse all of these things, and then you can do that. So that saves, all that is I saved this string of letters into a object called output directory. Then I want to use this command, set working directory, set WD, and create working directory. And that will now be my working directory. All right. And so now I want to import a file, df1 equals read.csv, file choose. And then if you use the file choose, it opens up a window. Alternatively, if you can't be bothered, you can just simply type in the name of that CSV file, which I've already saved, and I'm just going to import it like that. So df1 is now this data frame that we saved from that CSV file that we had before. Is everyone with me so far? Yeah.
For setting your working directory, is it the same as doing file and project and setting your working directory that way?
I don't know.
Okay.
I've not used the project before.
Okay, that's why I think you should do it that way.
Yeah, okay. Yeah, it sounds like it would very much be the same way. Yeah. Any other queries?
Sorry, we have to restart it before.
No, you don't. You don't have to. Can you please go over once more setting up working directory? So essentially I went over here and this is my, okay, so first of all, I already saved, before I started this, I went and I downloaded the Google Drive course code file and I put it on my desktop. Then I went and copy pasted this. I copied that and then I put it into my RStudio. I called it output directory. I typed this in, output _ directory equals open brackets that, but R, because it's special, it only likes /, and then I changed all of them to /, and then I called it that, and then F9 to run it, and then I set the working directory. So now every time I ask R to look for a file, it will look for it in that folder. And then if I want R to save something, it'll save it in that folder. So df1 equals, now I'm going to save, I'm going to open up df1 by doing this, read.csv. And so now if you just go df1, it will output all of these numbers. And if you go view df1, you can also view it like this. You can view it, go down, and then view it. So that's what the view thing does. Then you can also use str, view the structure of the data set. Str df1 is quite useful. And then summary df1 is also quite useful. So if you look at sex, the median value is 1, which is very useful, right? I'm being sarcastic, sorry. Yeah, some of the numbers are useful. And head is also quite useful because you just look at the head of the values. You just want to look at a few. And tail, you just look at the tail end. Cool. Okay. Yeah, so now notice that if I go structure df1, do you see how ID is an integer? Now, what that means is person number 1, let me just go back out and open up that Excel spreadsheet. No, you know what? Let's just view df1. If I view df1, this person is 1, this person is 2. Now, R is going to treat this as a continuous variable, as if ID was the same as height. This person's value was 1, this person's value was 2, this person's value was 3. That's not really what we want. We don't want that. We actually want it to be a factor variable, i.e. a nominal variable. And so that's why we can use this. So if you just went df1 $ID, it just creates that. And so if you do as.factor, it creates it all into a factor variable. And then so you just run this to create everything as a factor variable. And also the sex variable, if you look at the sex, well, it just is a load of 1s and 0s. So again, yeah, you want to change it into a factor variable. df1 ethnicity data, change it into a factor, change it into a factor. And notice that right now, if you go view df1, oh no, there's no capital D, df1, it is in the wide format. Do you see how we measured their systolic blood pressure at 9 a.m., at 12 p.m., at 3 p.m., at 6 p.m., at 9 p.m. We're making this go wide. This is the wide data format, and you can't, R prefers the long format, and so that's the answer an earlier question. Does it matter about the wide and long? Yes. R, generally speaking, prefers the long format, not the wide format. So what you can do, you can use tidyr to gather all of these variables and then change it into a long format. Alternatively, when you're organizing your data in the first place, you could just gather it in the long format as well. And then it changes it into, using that command, it changes it into the long format. Notice how the time is now sys09, sys12, sys15, systolic 18, systolic 2100. So now this is now the long format. So df1 is the wide format, and df1 long is the long format. Do you see how ethnicity stays the same for person number 1? Age stays the same. Everything else stays the same except for the time and the systolic blood pressure. Okay. So now, how do you produce some quick graphs? You can just simply do histogram of their age. And so as I was saying, that's what a histogram looks like. You can also, and now look at the frequency. Okay, so now if I did this, why did the frequency increase? Why did the frequency, so if I just go back, this was when I did df1 $age, whereas this is when I did df1 long histogram age, but then the frequency changed. Well, if you view df1 long, you can see that when I look at age, it means that there are 5 times the number of 60-year-olds, 5 times the number of 45-year-olds. And so it's just the nature of the data that's just been slightly messed up. So, yeah. You can also do these, they're quite a little bit complicated, but if you just think of this, let's just go, when you see so many brackets, always go for the smallest element first. df1 $treatment is a series of ones and zeros. Remember, this experiment was where we gave some people drug X and some people no treatment. And so if we just said DF1 treatment, you can see the first 100 were given the drug X and the second 100 were not. So now if we just want to look at the people who received the drug X, now you could change it into true, false. And then if you look at DF1 brackets age, and now if you think, okay, so actually we only want the DF1, the ages of people who received true. That's how you can get, this line is basically saying, I want a histogram of the people who received drug X. And so that's one way in which you can do this sort of data. And this second line was, I want the ages of people who didn't receive any treatment. Does that make sense? Nod your head or shake your head. Okay, box and whiskers plots, similar idea, a very simple command called box plot. Looks like that. And then similarly, if you go df1 long age, okay, well, the numbers don't change. And similar, scatter plot. And then scatter plots, you can plot, so from person 0 to 1 to 100, you can look at their age. Now you can, do you remember that tilde sign? So this essentially is saying the age is going to be on the dependent variable. Age is a dependent variable, sys09 is the independent variable, and each dependent variables typically go on the X or Y axis. Dependent variables typically go on the Y axis, and so it's always Y against X in this format. And yeah, that's what it does. And now that was a continuous versus continuous variable. Now let's do a continuous versus discrete variable. So we can look at the ages of the people who didn't receive treatment and the people who did receive treatment. So with a simple line of code, you can very easily look at your data in a more holistic point of view. You can look at it, view it in a lot of different graphs, and that's one, well, it's just a nice thing about R. Right, so I think I've gone through, open the data, okay, import the data, observe it's in the wide, change it along. All right, so now we're gonna go about creating, okay, so now we're gonna go about creating a graph from scratch, and with the intention of publishing this graph. So summarize the data for plotting purposes and produce ggplots for publication, showing patients' systolic blood pressure over the course of the day, separated by drug X versus no treatment. How many dimensions of data are we talking about? Well, there's time, there's systolic blood pressure, and what else is there? Yeah, good job. Treatment. I can hear you thinking it in your heads. So yeah, so there are three, essentially this will be a three-dimensional plot. And so the first thing you want to do is you want to summarize the data. So first of all, actually, to be fair, what I personally prefer to do is I always like to draw what I want the data to look like. Oh, goodness. Dare I do this? Basically, I'm gonna say I want this data to look like and then so now we have time. Why am I doing this? This is a time. Oh, that's why I'm not doing that. Okay, that's time. And then this is systolic BP. Well, that's not much better. Sys BP, systolic blood pressure. That's what I'm trying to plot, and I want to plot it over the course of the day, separated by drug and no treatment. Now that I've got this, what would people like? How should I, so this will have essentially two lines. Let's say blood pressure modulates like this for the people with treatment, without treatment. But how do I differentiate these two? How should I differentiate them? What's a sensible way? Yeah, you can do color. You could do dotted line versus, you could do all sorts of things, yeah? But also remember, this right now is only got the, it's only got a measure of central tendency. We also want dispersion. So we also want like error bars. So yeah, we're gonna also have error bars. And just imagine that I'm not going to be bothered drawing error bars in for everything, but there are also going to be error bars. We want error bars as well. So yeah, that generally speaking, on a piece of paper, I just draw out what I want it to look like generally. Now I note there are 3 dimensions, one on the X, one on the Y axis, and now a color dimension as well. And then don't forget, I also want error bars. So first of all, you actually need to summarize the data, and you need to be like, okay, well, what's this value? Because in your data set, in your data frame, you have all 100 values. You actually need to summarize the data first. And this is what this code does. So using I'm just going to call it, let's just freestyle, the summary df1 equals, I'm going to use this ddply command, and I'm going to use the dflong command. And I'm just copy pasting it, but I'm going to against time and treatment, and I want it to summarize, and I want to create something new called sysbp mean. Okay, let's just run this. Essentially, right now, if you just look at df1 long, it's got all the data points, it's got everything. However, you don't actually want the individual ID variables. You only want a summary. You just want an average of all the 9 o'clock values of systolic blood pressure, and you want to average across ID. Essentially, you want to get rid of this first column and collapse it down, right? And so this is what this command is essentially doing. And now if I look at df1a summary, that's what it does for me. I have my time at 9 o'clock, at 12 o'clock, at 3 o'clock p.m., 6 p.m., 9 p.m., and the groups with treatment and without treatment. And I have the mean systolic blood pressure, and then I also have the standard deviation systolic blood pressure, and also the standard error blood pressure. So that's what that command does. Are we with me so far? Okay, so what I'm doing is I'm using descriptive statistics to summarize my data. Rather than plotting all of my values, which is a bit overwhelming, I'm summarizing the data using that command. Now, first of all, with ggplot2, I've not really talked about functions, but I'm just going to go straight into it. So the data frame that I'm going to use is the df1a underscore summary, and then ggplot likes to use something called aesthetics, AES, and within the aesthetics framework, you have an X value. So what was on the X axis? What do we remember? Time, all right? Can I just call it time? Yes, I can, because if you look, it's all lowercase, it's all lowercase time. And then the Y is, what was the Y? Systolic blood pressure, but which factor are we going to call it? SysBP underscore which one? Mean, standard deviation, or standard error? What do we think? It's going to be the mean. We're going to be plotting the mean. Yep. And we also want color equals treatment. Okay. That is what we want. Now, ggplot now recognize this. If I run it, it will recognize that. However, it won't actually plot anything, and that's nothing will plot. It's just recognizing that, because now we have to add geomes and we have to add aesthetics to this. We need to add, and then so if you just simply go geome underscore point. Okay, I'm just going to enter this to the next one just so we can see all of it. If we do that, and then it just creates these points. That's quite nice. It's got the 9 o'clock, 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. So that's what we've got so far. Well, I'm not very happy with that. So what am I going to do? Well, I want a geome underscore line as well. I also want a line. Oh, okay. Never mind, I don't want a line. What else do we want? We want the color scale. Let's do the X. We want to change the X axis. So I want to call the x-axis name as time of day, and then the labels I'm going to call 9 a.m., 12 p.m., 3 p.m., 6 p.m., 9 p.m. Does that look about right? Oh, okay, I made a mistake. Discrete value supplied to continuous scale. Do you see how the time, if you look over here, is time going to be a discrete or continuous variable when I lump it like that? Oh, sorry. If I lump it like this, is time a discrete variable or continuous variable? It's actually a discrete variable, even though time technically is a continuous, but in this case, it's a discrete. So that was my mistake number one. I need to go scale x discrete and then run that, and that should do it for me. Now the y-axis, I want to make it nicer as well. So I do scale y, and now this time I definitely know it is a continuous variable. The name of the title, I want to call it systolic blood pressure, millimeters mercury. And actually, I'm going to say the limits, I want it to look a little bit bigger. So let's go from 70 to 120. So the limits, the lowest and the highest limits is going to be like that. Yeah, let's just do that. Let's just run that and see what happens. Yeah, that's shaping up quite nice. Yeah. However, what if I actually want these mini ones? Like, what if I want 5? I want breaks. Now, then I could do 70 goes to 120. But the break, if I do that, let's just look at that. The breaks, it'll just mean that there's only one break at 70, one break at 120. What instead I want is I want a sequence of numbers. So let's do 70 goes by 5. Does that work? Let's see, 75. No, that doesn't work. Okay, never mind. Let's do sequence. Oh, what the? Interesting. I've never done this before. Interesting. Ooh, okay. Okay. Oh gosh. View panels. Show all panels. There we go. Now where was I? Template code below. All right, we're over here. Now, if we did breaks, if we did sequence and by 5, if we did just the sequence, the SEQ is a function that I am aware of, 70, 75, 80, 85. So that's just what's going to generate this on the y-axis to be like that. Now, I don't know about you, but I don't actually like the gray background, so I'm going to use something called theme classic, theme_classic. And then that's going to do something like this. And that's a bit nicer. Now there's also the color problem. I don't actually like the color, scale, color, discrete. And then I'm going to call it name is treat. No, I'm just going to call it nothing. The name is nothing, but the values I want it to be blue and red. Sorry, red like that. And then you can see, okay, sorry, this should be scale color manual, And then you can see how this will turn into a more blue-red distinction. Now I also want there to be lines. So I did want there to be lines. So we also need group actually over here. Group equals treatment, color equals treatment, and with the group, then you can do geom_line. Oh, geom spelled correctly. And now you have that. Where did my theme classic go? Ah, thank you. Thanks. Yeah, and then that happens. So now I've got that. Now what else do I want? Maybe I want these to be bigger. So maybe I can just add in a size equals 2 and a size equals 1. And there, that can be bigger. And then what else do we want? What else is good? Error bars, that's right. So we want to add error bars. Now geom_error bar, and then we'll also use the same df1a sum. df1a sum, aesthetics x equals time as well. Y equals sys bp_mean. No, sorry. So when you do error bars, you need to specify the minimum value and the maximum value. So y min equals sys bp underscore. So I'm just going to type in so you can see it in the back and the down here. I'm going to go sys bp underscore mean minus sys bp underscore se. Let's use standard error for today. Y max equals sys bp underscore mean plus sys bp underscore se. And once we've done that, yeah, let's have a look what that looks like. Mapping plus aesthetics. Oh, okay. I also need to add group equals treatment, color equals treatment. And you can see it's getting quite long, so I'm just going to break this down so I can actually see it in one screen. Okay. Let's just aesthetics. What's x equals time, y equals this. Okay. And this is part of the fun of dealing with this sort of stuff. Maybe I don't need that. Do I? Okay. Run error mapping must be created by AES. AES is x equals time, y min, y max, width. Okay. Error bar. How does this work? Okay. I'm just going to put this above it. Maybe that might sort it. Then add that. And then close that. Okay, well that didn't work. Well, then.
You've got the df1a sum again, and you don't need it.
Right. Could be it. Right, thank you. Perfect. Thank you very much. And then, yeah, so that's what it looks like. The width is a little bit long, so I might do width equals 0.25. And then that makes it nice and short. So let's call that, and then you can also add some themes. So I might just copy some of these themes in. Theme, the axis text element, I want it to be size 10, title 10, and I want the legend to be on the top. And then there we go, there is a graph. Okay, let's actually call that treatment values blue red. So let's call this temp graph 1 equals that. And then when you have temp graph 1 equals that, you can run it and it brings out that. And now all you got to do is gg save file name equals my first graph.png or .pdf because it's a vector file, and then plot equals temp graph 1, size width equals, depending on how big you want your thing, I think typically it's like 6 centimeters, height equals 6, units equals cm, and that could be now temp graph 1. I need to call it temp graph 1, and then I gg save it, and it's saved. Now where did it save? Where I put my directory, yeah. And so therefore it's over here, my first graph, and then there's your figure. And then you'll realize that looks really ugly and you have to go and fix some more things. And then you go back, change the sizes and rinse and repeat, and then you submit to nature, and then you win in life.
Can you say that as it appeared on the screen, or is it?
I don't recommend it because what you see on the screen will invariably be due to many different things, like your resolution of your computer. Yeah, so you want to use gg save to do it, yeah, ideally. So I've kind of highlighted you through, gone through sort of what you can expect when you're publishing this, and then over the next few seminars we'll go through the different statistical tests you do, and then the different stats, and then adding the asterisks. Yeah, we'll go through that, and that's sort of what you can expect from this graph, this course. Cool. Yep. Great. If you have any other questions, I'll stay behind, but thanks for your attention, and yeah, hope it's been helpful. Thank you very much.